Hello students, today we will discuss the generation of long nonlinear sequence. It is its importance also we will discuss little bit, and their usage in the spread spectrum communication system needs to be understood. Why we are suddenly coming here, because almost with the background of the understanding of Galois field and polynomials over the Galois field, the generation mechanism, understanding of the characteristic polynomial. Now, we are in the situation of understanding the way the codes are generated, and there are two different kind of the codes that are usually used in spread spectrum communications. There may be a short length code, there may be linear code, there may be also long sequence codes and long nonlinear sequence codes. So, let us see today what are the corresponding advantages, disadvantages of all these different type of the codes. Long sequence code or the long code in a spreading sequence, they are defined in a way that the period of such codes should be greater than much greater than the symbol period. Then we can say that they are the long sequence codes, whereas the short sequence codes or the short codes are defined as the period having the period which is much less than the symbol duration, data symbol duration. See, if you are having a short sequence code, then it will be very easy to intercept. That is, the jammers can very easily crack the code by observing your code pattern over a small duration of the time only. It is just a matter of time of observation. If I observe this for a pretty good amount of the time, easily the pattern I can regenerate. I can make some assumption of the pattern and then easily it can be regenerated. And once actually the code is cracked, and if I get the code, definitely it will be very easy for a jammer to jam the communication system. And now it will be very easy also to extract your own information, that you are transmitting on air, and also to jam the information, so that receiver does not get, intended receiver does not get the actual information. That is a problem of having a short length of the sequence. What is the problem of having a linear sequence? If it is a linear sequence, then they are inherently susceptible to the mathematical cryptanalysis. So, the hackers who are also who are also actually a point of our interest in such kind of communication system design, especially today, then this susceptibility towards a mathematical cryptanalysis is not a desirable criteria. It is not at all desirable for the system design. So, we are having both the problems, problems with linearity of the codes, also having a problem of having short code sequence length. In order to avoid the both, we usually prefer to go towards the long nonlinear pseudo noise sequences or the PN sequences, and the programmable code generators, that which are very important now to understand. Remember, this long code sequences with nonlinearity involved in it, they give a very high level of the security involved. Now, it is the designer's choice based on the level and the priority of the security demanded in the design system, how actually we will choose and will do the compromise between the length of the sequence and the nonlinearity involved in the design. So, if the security is acceptable, then short or moderate length pseudo noise sequences also we try to utilize, because if short distance, if the length of the sequence is really long, you cannot actually utilize it for a very rapid acquisition. For long length, your acquisition, synchronization acquisition in the receiver also needs some more time. So, convergence of the acquisition algorithms, they are not so fast. So, if you are going towards the security, then you have to have a compromise over a long acquisition time. but if you are fine enough with the moderate rate of the security, then it is the short and moderate length pseudo noise sequences are preferable for very rapid acquisition, burst communication, as well as the multi-user detection in a wireless communication scenario. The multi-user detection or MUD is a very well known research topic, where the design of the sequences is the most important research criteria for developing for establishing a good outdoor wireless communication system. The algebraic structure that till now we have learned for this linear feedback shift register, the name itself, the linear, signifies that the linearity is involved in the whole structure, because this is only the XOR gate involved. If you remember, only the XOR gate is involved in the feedback logic, and hence it is very easily susceptible to the cryptanalysis. So, the structure till now that you have studied is not enough to generate a very high secured code. So, let us see let us see the criticality in terms of the mathematics also. Say, let us see denotes some column vector of the m feedback coefficients. So, these are the coefficients that we have designed, and small m is the number of the stages involved in the linear feedback shift register. And these are the column vectors, and so you understand that the way we have in the high speed form of the linear feedback shift register, these are the switches, the location of the switches, the typical state of the switches, whether it is equal to 1 correspondingly tells that typical stage is contributing to the feedback logic. If its value is equal to 0, it is not contributing. The T here is now defining the transpose. Now, the bits that are sequence bits that are produced by the shift register, let us write the column vector of those m successive bits that are coming out. Here is given by the vector a I, where a I will be the a I, and a I is coming up with the a I plus 1, a I plus m minus 1 dot dot dot. Now, a I is a vector, so it will be bold. And now, let us understand that capital A I is a m cross a matrix, where in every column that we have put, it consists of a vector a j, where a j is looking like this. So, its transpose means it will be turned, and then hence it is written in a column format. But this j value starts from the I, and it goes to I plus m minus 1. So, here if I starts with the j value is equal to I plus m minus 1, if I start, then slowly I will be ending up with the value of I plus m minus 1. This value of I should be replaced by I plus m minus 1, and hence the last value will be I plus 2 m minus 2. What I am doing? I am just shifting, I am just replacing and substituting the value of I by the value of I plus m minus 1, and hence I should end up with I plus 2 m minus 2. The next module, the next column, sorry, which would start with I plus m minus 2, and if I go by another I plus m minus 1 step, I will be ending up with I plus 2 m minus 3. In this way, if I start, and I will be ending up with the value a I, who will be where actually I will start, and I will end up with I plus m minus 1. And you can see the sequence such a way that it is something like the invert of this starting with the first having the value of a I m plus m 1, and then finally seeing the last value seeing as an a I, and hence the corresponding column values are coming up. So, fundamentally it is generating a m cross m matrix, and a I is denoting that matrix. We understand, and please recall that the output is having a linear recurrence relation given by this, where the clock pulse value is greater than equal to the stage number small m. And hence we, from following this recurrence relation, we can also write that any I plus mth value will have some a I multiplied by c, and if this A I multiplied by C, this C is another feedback coefficients, it is multiplied by the feedback coefficients and you will get the value of A I plus mth stage at the output. Now, as this matrix is of m cross m, and if I see the twice m consecutive sequence bits and if it is known, then A I and I plus m, A small I plus m, they are completely known for some value of the I. And if I believe that this matrix is invertible, then you can easily get what should be the setting of this coefficient C by this formula. So, now what is the situation that you mean if the sequence length is short, if you observe it over twice the m bit period, what is the m sequence and the bit period. So, you will have a complete knowledge of this A I and for some value of the I, and if you can if this matrix is invertible, then definitely I can get the setting of C matrix. The setting of C matrix is nothing but the setting of the feedback path. So, now you know the whole everything about the design, the way the key is generated, what are the typical C values, you understand the whole capital matrix, you have a relation of the initial stages. So, you can reproduce the code easily. Shift register sequence is completely determined by the feedback coefficients and any state vector. Say I have the small m successive sequence bits determined by the state vector, by a state vector, and 2 m successive bits provide the total information about how to reproduce that output sequence once again, unless A I is invertible. So, if A I is not, unless A I is not invertible, if A I is invertible, then this information alone is sufficient to give you the whole information to regenerate the circuit and regenerate the code. And in that case, actually hardly one or more additional bits you may be required for you to understand if your A I is not invertible also. So, for a binary sequence which is having a period of say n, that can be always generated by some n stages linear feedback shift register by connecting the output of the last stage to the input of the first stage as shown in this figure 1, and by inserting the n consecutive bits of the sequence into the output sequence that we have shown here. So, this is a very fundamental stuff, that if I understand that there are the n stages of the feedback, because there is a period of equal to n. So, if I put the n memory stages here, connect the output to the input directly, and if I know the insert the n consecutive bits of the sequence that we have observed here. So, automatically the sequence will be generated, and only part is that you are involving the large number of the stages, that is all. But cases of the, if the jamming is very important, your target is to jam somebody, you will not mind of putting the large amount of the hardware to regenerate the circuit. You need not to generate, maybe actually in the transmitter this sequence was getting generated by only 3 stages of the shift registers. Here you are involving all n stages of the shift register, that will be the difference only. Now, the polynomial which is associated with one period of the binary sequence, the generating polynomial which is associated with that, we have seen earlier that this is given by a I x to the power I. Now, we also understood that the degree, this capital G x, which is a generating polynomial which is given by also g x by 1 plus x to the power n in the last module. And if we see that the greatest common divisor of this g x and 1 plus x to the power n, it is not equal to 1. So, then the degree of the denominator here of the g x will be always less than n, and therefore, the sequence that will be generated by this generating polynomial g x, it can be generated by a linear feedback shift register also with very few stages of the n. So, the condition is that if this there does not exist a greatest common divisor between the g x and 1 plus x to the power n, and the degree of the denominator is less than this n, then actually the generation, the sequence that is getting generated by this generating polynomial, they can also be generated by the stages which is less than n. So, shift register stages that you are involving to generate the sequence will be less than small n. And by appropriately initializing the state, we can be determine the coefficients of the numerator also. And the linear equivalent of this sequence is always called of any linear shift register sequence with the very few number of the stages. We call it is the linear complexity of the sequence, and if the linear complexity is equal to the small m, then the linear equivalent of the observation of 2 m successive bits can be observed by the expression the last we have seen, we have shown in equation 1.64. So, fundamental part is that if you see that the generating polynomial which is given by g x plus 1 plus x to the power n is not having any GCD between g x and 1 plus x to the power n, GCD is not equal to 1, and you see that the linear figure register with the very fewer stages than n can be generated, can be utilized to generate the sequence if we are having the value of this n, if that degree of that polynomial 1 plus x to the power n is less, I mean the denominator stuff is less, then we can generate it with a fewer number of the stage, and because of that, which is defined further by the linear complexity also. Look, one part is really clear. If we increase the length of the sequence, or if I that means the period is increasing. Period increasing means the length of the sequence is increasing. If we increase the length of a sequence, definitely the security increases. But there are some practical limits to the number of the shift register stages that we can utilize for the generation of such sequences. So, involving a huge number of the shift register sequences in the circuit to generate a long sequence is not at all a practical practically advisable system design. So, what we can do is actually we can equivalently generate the non-linear. Actually, we are trying to improve the secrecy by increasing the length, but if the equivalently we can improve the secrecy if we are giving the feedback non-linear. So, better you do not go improve the security by means of length, you improve the security by means of improvising the non-linearity inside the feedback circuit. So, it will also serve the same purpose, and otherwise you do one thing actually. So, output of the 2 or 3 stages that can be also fed back before taking the output directly from the last stage. We can actually take the output of the 2 or 3 stages and then we can add them into a nonlinear circuit and nonlinear device, which will from the output of the nonlinear device we can take the output. Output of the nonlinear device can be the final output, I mean. So, either way, either you do the improvised nonlinearity in the feedback path, or you improvise nonlinearity by combining any 1 or 2 stages of the feedback shift registers, feeding them inside a nonlinear device and take the final output from the output of that device. And we will see this kind of the structure, both the structures where actually multiple output stages will be fed to a nonlinear device. Maybe here you have taken an example where we will feed it to an AND gate to produce the output sequence, and another nonlinear generator which is coming next. This is the circuit. A nonlinear generator is shown in the figure number 2a, where we are having 3 stages. This values is kept inside is nothing but their initial values, and this was a well known structure as we were discussing since beginning, that the stage number 2 and stage number 3 is contributing in the feedback path. We has improvised nonlinearity not by changing the feedback architecture but by taking the output of the stage number 2 and stage number 3 and feeding it to an AND gate, and final output is taken from here. If you see actually the structure of the code that is getting generated at the output of the AND gate, and you will be able to see that the sequence that is getting generated is that can be also be produced by its linear equivalent, where the total number of the stages that is getting generated is equal to 7. Here, from here you will be able to generate 7 stages, and here actually we have kept all the 6 stages n minus n number of the stages. The repetition is 7. So, here you will keep 6 number of the stages here, and all the stages if I linearly combine in the feedback path, and if we feed it back to the initial stage, we will be able to see that both the circuits are generating the same sequence. So, idea is that instead of giving all the very big number of the very big circuit and involving huge number of the stages to generate a nonlinear sequence, we can come back to a minimization of the number of the stages involved by adding one nonlinear device. Please do this exercise at home. First see the sequence generated here, and also by the default, by given this circuit with this initial situation, try to see actually what exactly is the sequence you are getting, and if you see that both the sequences are same, then definitely both the structures are also equivalent. So, these are some explanation that I have already told earlier. See, when a long linear complexity, when a larger linear complexity is definitely required, because if we wish to give a high value of the security for the cryptographic integrity of a sequence, say. So, remember it is not true always that if you are having a very long sequence and such a very even distribution, suppose there are only the long sequence it is, and it does not mean that only having a very long sequence it will improvise actually the very good amount of the linear complexity involved. It should have some other properties also. For example, the number of the ones and the number of the zeros that you are generating in that sequence, there should be very well balanced between the zeros and ones. So, contiguous ones and contiguous zeros, that should not come also. So, the statistical property of that sequence is also very important when we are talking about the linear complexity, and the sequence will be very weak. See, for an example, if a long sequence have so many number of the zeros followed a very single one, and then again actually long number of the zeros. So, the linear complexity may be very high, but the signal is very weak, very easily it can be cracked. So, another example of this generation of long nonlinear sequence we will take in the next slide. Let us see. So, here the idea is suppose you have two different set of the shift register sequences. The shift register sequence 1 may have let us first consider that both are having the same number of the stages, are equal to same, initial conditions are not same, and what you are doing is you have involved a multiplexer in the code generation process. The shift register output of the first one, or here it is as shift register number 2, he is giving first some code sequence. Okay. So, the output you have tapped the output from certain stages of this shift register architecture, and whatever the bits that are getting generated for a typical clock pulse, you have taken it and you are reading it as if as a address. So, that address the multiplexer will send to the shift register 1 architecture. According to that address, the bits that should be picked up from the shift register stage, and that will be directly connecting to the multiplexer and coming out as an output. For example, suppose this value of the m is equal to say 8 for example, and we have tapped the value from stage number 2 say stage number 5 and say stage number 7. And at a particular instant of when a clock pulse has arrived, I am seeing the values of 2, 5 and 7th stage output is such that it is giving a value of 0, 1, 0. In this shift register also they are having the 8 number of the stages. So, the shift stages are like this, going from 1 to say 8 number 8, and this is the stage 0, 1, 0, that is the stage number 2 value is getting asked for. So, the step will be from the stage number 2, the whatever the value at this moment when the clock pulse came here and when you gave the clock pulse here, whatever the value is generated at the output of the stage number 2, now it is getting connected directly to the multiplexer and coming out as an output. So, if you keep for each and every clock pulse, you will keep on changing, generating the new addresses definitely, because based on the initial condition of the initial state condition of the shift registers, you are generating these values. Is it clear? So, whenever you are generating these values, new values you are generating, based on that either the stage number 2 or stage number 1 or stage number 3 or stage number 7, you are picking up the values from the different stage outputs. So, the generation of the address of the stage is done by the first shift register, and the typical actual output is taken from the second shift register architecture. The value, instantaneous value that is getting generated is taken out as a code bit. So, if I now observe over a say pulse of say 10 or 15, I will get a series of the bits coming out from the different stages output of the shift register 1, and that is my generated code. Okay. So, now the good part of it is whenever your generated code is like this and its period it needs to be controlled, you can actually do that easily, because it may happen that either you are not taking the variable address for the variable one, or you are may have a situation where the address whatever you are generating, it is always equal to 2. So, always you are getting stuck to 2, but for each and every clock pulse the value output of the 2 is varying, hence actually the generated code structure will be something else. So, either you keep on sticking to the typical address in the shift register 2 and and then ping a typical stage output, and on the arrival of the clock pulse, continuous arrival of the clock pulse, keep on checking that output and you pass that output through the multiplexer and generate the codes. Or for each and every clock pulse that is coming here and here, for each and every clock pulse you keep on changing the address, you make the address variable, and then you shift actually the point where from the output should be picked up, and that can also be code. So, whoever is whatever be the architecture required for the kind of the secrecy, actually you can design it accordingly. So, here you see instead of the AND gate, the multiplexer is giving you the incorporating you the nonlinearity in the whole architecture. It need not to be done exactly the way I have explained. This is just an example how with the help of multiplexer and two different shift register architecture you can do it. It may also happen that it can be vice versa. I mean, you can have at one shot you generating the address from here and picking up the value from here, and the next cycle you are generating the address from the first shift register and then picking up the value from the shift register 2. So, the what way you will combine is completely your design constraint, but this is one example, and there are several examples like that, the way you can improvise the nonlinearity inside the circuit that will not increase the number of the stages in the shift register sequence generation, but it will definitely help you to improve the security level of the circuit. But remember one thing, whatever you are doing, I mean shifting logging into a single shift register and taking the value from here, or you keep on changing the changing the address for each and every clock pulse, or even changing the shift register. So, where from the final output is taken out, but always check finally the generated codes auto correlation as well as the cross correlation property, because this auto correlation that we have learnt already, that the auto correlation as well as the cross correlation properties and the related power spectral density of the generated code, they are actually really very important issue in terms of the synchronization aspects and that code acquisition, code tracking in the receiver circuitry. You should not generate a code because you are trying to improvise high security. Do not allow and generate a code such a way that in its power spectral density there are several high value peaks. Then you will definitely you will get a false lock in the receiver. So, security will be very high maybe, but recovering your own signal may be in under tie, because you are unable to do any code synchronization in the receiver with such kind of the generated codes in the receiver, and hence your own detection process in the receiver will be hampered a lot. So, there is a again a trade off between the high secrecy involved and the level of the complexity that you are trying to improvise in your design towards the generated power spectral codes power spectral density and the peaks that are spurious peaks that are coming with respect to the main peak. So, we hope that I hope that we have covered lot about the sequences and the sequence generated. Long nonlinear sequence generation was the last part of the code discussion about the codes sequence spreading codes that are involved, and in future I hope you will be able to generate your own codes for while designing such kind of the systems.